Welcome back. The next step of electrochemistry. So we are thinking about a simple case where we have a cell. So let's have a kind of cell that you might be familiar with a salt bridge. So that would be a piece of paper soaked in salt and two solutions. Let's take a Daniell cell. So this would be a piece of zinc, Zn, and this would be a piece of copper, Cu, and they would be in their respective solutions. So this has got zinc 2+ in it, and this has got copper 2+ in it. Let's go to this pen. So we connect them together and we measure both the current and the voltage. So we have, let's have a way of doing that. So we need an ammeter and we need a resistor with a voltmeter across it, V, so we can vary the voltage, this value of this resistor. That changes the current. Let's make them blue and green, so green for zinc. So typically what we will see is this zinc 2+ will dissolve, or the zinc will dissolve as zinc 2+, the copper 2+ will plate on, and the electrons will move from the zinc metal into the wire across and into the copper. But now what we're interested in more is the voltage and the current. So from chemistry, what we discover is that the voltage of this reaction, if we put in a nominally infinite resistance here, so we have no current flowing at all. If we measure the voltage at no current, it doesn't matter how big this electrode is, because we're not taking any current, so it makes no difference. If we allow that to happen and measure the voltage, what we're measuring is the difference in energy, or the difference in energy between the electrons here and the electrons in this electrode here. So effectively we're measuring an energy difference between the two. If we apply a small resistor here and measure the current, a lot of current will flow and the voltage will drop, and that is because the zinc can only dissolve at a certain rate and the copper can only plate at a certain rate depending on the size of the electrodes. So drawing that out in a more general term, in a more general case, we can say if we allow the current to vary, so we vary this, if we allow the current to vary and we measure the voltage, we can, I only have positive ones I see, we can measure the voltage of this cell and the voltage as we increase the current. So we, in this case, our current would be the x-axis, but I don't like it that way around. So we're going to cheat and put the current on this axis, although it's the one we're varying. V in volts. So if we increase the current, the voltage goes up in some way. Which way is it? It's this way. So if we increase the current, the voltage goes up, but at some point we can't increase the current any further because we have saturated the case. The zinc is leaving as fast as it can, or the copper is depositing as fast as it can. It's normally this side. So then we will have some kind of tailing off. That's the way it will do it naturally. If we apply a voltage source, which is what we were doing, we can force it in the other direction as well, or we can push it further up in this direction, because there's no reason why we shouldn't force it more with this voltage. So what we're going to do is we're going to take this voltmeter out and instead insert a power supply, and the power supply can be positive or negative, then we can vary the voltage and then my graph becomes right. If we do that, we can see that there's a voltage at which the current is 0, and below that voltage the cell goes backwards, the copper dissolves and the zinc plates, or the zinc tries to plate anyway, and we go the other way and see something. Let me draw it not quite even. And we see something happening. So now I'm going to turn this cell around, because that is more like we have in the experiment that we're about to have. We're going to turn the cell around and change this one, put the copper cell on this side and have an iron one on this side, which is what our experiment is. So if we look at this, we've got the copper on this side, we've got copper sulfate, for example, in our solution. We've got a copper electrode, and if we look at this, we can deposit copper or we can dissolve copper. It's a relatively reversible process. So we can have a straight bit of curve because we can deposit the copper on this side and we can dissolve the copper on this side. Obviously it will curve off just like the others do when we have something happening that's hindering the copper leaving, which we'll talk about in a moment. And on this negative side, at some point we will make the concentration of copper next to the electrode so low, 0, that it can't get down any lower because it can't be less than 0, and then the copper 2+ has to diffuse to it, and it can only do that at a certain rate. So we reach a diffusion limit and it will curve away. We can't push it any further. This isn't a 0 slope, it does go down slightly because we can attract the copper from a distance, but it's not a very strong effect compared to this. So why does the iron stop dissolving? Well, we know when we see iron things, they're covered in rust, which is a type of iron oxide hydroxide, and so that should be a clue to us. So if we take a piece of iron, this is our iron, Fe, and we start to dissolve it, we're making ions in solution, maybe iron 3+, maybe iron 2+, depending on the potential and depending on the solution. Let's have a wire. And then we will have a concentration gradient between the iron and the solution. So this is concentration of Fe, let's have a 3+. It goes down as we go away from the surface of the iron because it's got to diffuse away, just as the copper had to diffuse to the electrode. The iron has to diffuse away from the electrode, and then we go back to our first semester physical chemistry. So if we take iron in water, Fe3+, for example, and we react it with OH-, 3 OH-, we can get iron hydroxide, FeOH3, but that's not the normal state of iron that we see. So this, hang on, this is AQ, this is AQ, and this could be AQ or solid. Let's have a solid AQ. It's somewhat soluble, but if we take our iron hydroxide, we can also dehydrate it to FeOOH, which is normal rust, standard rust that we see everywhere. That's the red thing that we see in wet rusting, plus H2O. That's the rest of these. So we can release water, it can dehydrate. This is a relatively common process in metal oxides and hydroxides. So we can see that we could formulate a solubility product for this. Solubility product is equal to the concentration of iron 3+ multiplied by the concentration of OH- cubed. We could put water into that, but the concentration of water doesn't change, so not in water anyway. So if we take the solubility product, we can see that the thing that is changing is the iron 3 concentration, and the thing that we can control relatively easily is the hydroxide iron concentration. So if we look at this, we can see that the solubility of the iron is related to the pH of the solution. So if we take an iron bar and we try to dissolve it in acid, it will have a relatively low concentration of hydroxide ions, and so it won't be able to make iron hydroxide. If it's in a basic solution, the solubility of the iron hydroxide will go down very rapidly because the hydroxide iron solution is cubed in the solubility product. This is a relatively low solubility compound, so its solubility will go down very rapidly as the pH goes up, and iron becomes reasonably stable. That's why iron reinforcing bars in concrete are reasonably stable, because the concrete is basic.